more applications of derivatives. Okay, so it's more applications of derivatives. So we've kind of done some of this stuff that we're talking about here before, but we're going to go over it sort of in more detail than we have. So we're going to talk about interpreting the meaning of the derivative in context, and this is going to be really important for your response questions on the AP exam, because you usually get some of these problems where you have to interpret that meaning. So derivative is the instantaneous rate of change of the dependent variable and dependent variable, is that your X or Y? It's Y. With respect to its independent. Independent variable, which is your X. Think about the notation that we use for this. For our derivative, sometimes we call it f prime of x. Sometimes we call it y prime. It's also dy over dx. The rate of change of the dependent, which is your y, with respect to the independent, which is x. Okay, so the units for f prime of x, so if you're looking at the derivative, the units for this is going to be the unit for f, or that's usually on your y-axis, divided by the unit for x. Okay, so another thing this is really important for is a lot of problems that you're going to get are going to ask you to give units with your answers, and if your units are not correct, then you can't get that unit point there. So on these problems, we're just thinking about units. We're not like actually working out a problem. So the function c equals f of t gives the cost in dollars of running a piece of equipment for t hours. So you're talking about cost and hours. The t here is like your x variable, right? It's going to be on your x-axis. So you would have t, which is hours, on that x-axis. And then you would be talking about the c, or you could call it f of t, which is the cost in dollars. Okay, so if we want to know the units for this, it is really very simple if you just keep it straight. It's just y-axis over x-axis. So in this case, it would be dollars per hour. Okay. Right. Units are just, because like if you think, if we have this graph here, if you're finding the derivative, what you're finding is the slope. Slope is changing y over changing x. Right. And this would be your f of t graph here. So if you take the derivative, your units are dollars per hour. All right. What about for f double prime? It is dollars per hour, because if we were talking about f prime of t, my x-axis would still be hours. But f prime of t, whatever that might look like, f prime of t would be dollars per hour here, right, if you're talking about f prime. So if you're taking the derivative of the derivative, which is your second derivative, you would be doing dollars per hour per hour. Or the other. Right, yes. So it can be, because you can think of it like this, dollars per hour divided by hours, which is like hours over 1. So that is dollars per hour times 1 over hours, which gives you dollars per hour squared. It really is not, both of these are correct answers. This is fine and this is fine. There is a general opinion amongst many teachers that you should use dollars per hour. The reason being is sometimes it's like cubic yards per hour might be what you're dealing with. And if you use the square, sometimes I see it much more common if you use the square to put the square in the wrong spot. Probably would not do that on this problem because dollars squared would not make any sense. But if it was feet squared, it would make sense to you. So, yes.
So is there a time that it could be like dollars per second per hour? Or would it like always convert it?
It could be dollars per second per hour, but I don't think you'll see that. They typically are going to stick with that same unit of measurement. There. Okay, so let's look at another example. The time it takes to run a distance is given by the equation R of D, where T is measured in hours, and D is measured in miles.
So miles over hours.
I don't think so. Because here, your function is R of D. So D is actually your independent variable here, the way that they have it set up, right? So D is independent. D stands for miles. So that goes here. This is D, which is in miles. And T, in this case, is your time. So that goes here. Which is, actually, I should go ahead and put hours there instead of time. It's not prime, but they're asking us about the prime. What's weird about this problem is that you normally would not do it this way. You would usually do miles per hour, right? That's what you would normally talk about. But in the way that it's given here, I keep messing this up. All right, so the units for R prime of D is changing Y over changing X. So it's hours per mile. It's the number of hours it takes you to go a mile. Yeah, so like if you're talking about the speed that you can run, it'd be less than 1. But if we're talking about how many hours it would take for a turtle to go a mile, that would, might take several hours. Even though we've caught some turtles at our house and it seems like they disappear really quickly. Probably because they've been terrorized by my children. A pig? Where do you live? Okay. It's really cute. Was it somebody's pet? It's not a... All right. All right, so if we are taking second derivative, what would we get here? Hour per mile per mile.
That's your rate at the certain part of the mile.
It is the rate that you're hours per mile is changing at for every mile. Yeah. So, but I purposefully did this one to where it was kind of backwards because I wanted you to see that you got to really pay attention to what's on that x-axis and y-axis. Yes. Right. And then your derivative is going to be the units for y divided by units for x. So the first thing you need to do is figure out what goes on x and what goes on y. And then, yeah. Yes. Yeah. Whatever. If they're giving it to you in function notation, what's in the parentheses is your x. Okay. So the length of a scarf is given by the function L equals S of t, where length L is measured in centimeters and time t is measured in minutes. What is the meaning of S prime of 7? So, see, so time is minutes, right? And it is on the x-axis. And length is in centimeters, it's on the y-axis. So when we do S prime, it is centimeters per minute. So S prime of 7, whenever you find the derivative of a number, it is that slope or rate of change at that specific time. So we would say at t equals 7 minutes, S prime of 7 gives the rate of change of the length of the scarf. In centimeters per minute. So if you're knitting this scarf at S prime of 7, if it's, let's say it's 5, well 5 would be, it couldn't be 5. But you would, if it was 5, you would be knitting that scarf at 5 centimeters per minute. It must be a machine. It could be anything. So your equation could be anything. What we're really focusing on here is understanding what it means. So, like, S could be any type of equation. It might be trig, it might be linear, it might be quadratic, it could be anything. So, it just depends on the equation. A lot of times these are calculator active, where you're not actually, like, working out the work by hand, but you have to, they either ask you to explain the meaning or they don't tell you the meaning. Instead, they would ask the question like, what is the rate of change of the length of the scarf? Or something like that. So where you got to figure out it's the derivative they're asking for. There. Mm-hmm. Yeah, S prime. Yes, it's S prime of t. Its units are going to be centimeters per minute. S is whatever graph you would have here. So S would the S is the length of the scarf. And then whenever you find S prime, it's the rate that length is changing. So like this is S prime. When we think of finding S prime of 7, let's say 7 was right here, you're finding the slope of that, so the rate of change of that. In this case, it's the length of the scarf. questions?
The actual graph of that would look like that.
You're right, it probably wouldn't because unless you unravel it at some point, it should be constantly getting longer. Or you could knit like I knit and then mess up and then have to pull some of it out and then start over. They're not knitting, but it's kind of similar. Not sure. I'd say it's most like macrame. Macrame is like a tie knots, I think. I'm not sure. All right. Example 4. This time we do have an equation. And so this is like something that they may ask you on free response. The equation h of t equals 5.42 plus 2.3 cosine of t minus 4. It gives the height of water in a swimming pool at time t. The height h is measured in feet and the time t is measured in hours since midnight. Find the instantaneous rate of change of the height of the water in the pool at 10 a.m. Yeah, that's the problem, and that's like what we're working on here. All right, so let's look at this part where it tells us what we're finding. We're finding the instantaneous rate of change. So when we see instantaneous rate of change, what are we looking at? Derivative, right? So the derivative of what? The derivative, this is derivative of the height of the water. Height of the water is h. So we're finding the derivative of h at 10. So what it's asking us to find is h prime of 10, which I believe this would be a calculator active problem. Someone, if you don't have yours with you. It would either be calculator active or they would leave the answer as cosine of 6. Now, this is a fairly simple derivative to take by hand, but since we can use the calculator, I am going to go put this equation into y equals. And I'm going to use an x instead of a t. And I might have to put a multiplication symbol right here. And so, calculator is something we probably need to work with a little bit more this semester because we haven't done a ton with it. How do I take a derivative? F3. Differentiate y1 of x, comma x. Now, this will take the derivative, and if the calculator can do it, which it can do it pretty easily here, it'll just tell you the equation. But if I want it to do it all in one step where it plugs in 10, what can I do? Not green button. All right, well, I have to hit something before I hit x equals 10. The bar. I have to use this bar right here. X equals 10. I'm going to hit the green button before I hit enter. And so I get 0.643. So it's about 6.43. Now let's think about units, because a lot of times these problems are going to ask you for units. So what is on the x-axis? Time, and it is measured in hours. And the y-axis is height. It is measured in feet. So this would be feet per hour. And since this is positive, it would mean that the height is increasing at that rate. If we had a negative, then it would mean the height is decreasing. Time is usually on the x, but there is that weird problem that we had a couple back where you had hours per mile. But usually time is on the x-axis, but not always. It probably means like it rains and then it evaporates and then it rains again. Yeah, and this is a cosine, so it's going to be repetitive there.
Or there could be like hose.
Yeah, they could be filling the pool up.
Yeah, like our pool. Drain. It has a hole or something and it drains.
Does it? Oh, when we get to related rates, I've got the perfect problem that we might need to address at the Elkin pool. Then, if that's the case. All right. Okay, here's our next one. All right, so this equation gives the weight of sand in a storage container after X days, where weight is measured in tons. Okay, so it asks us to find S prime of 15, and using correct units, explain what that means. And then we got to do S double prime and explain what that means. So let's start by just putting this into y equals. Not always, but lots of times these are calculator active questions. So it is pretty common to see these where you don't actually have to do.
I could not do it if it was not calculator.
You should be able to if it's not calculator active. But, because what is the derivative of e to something? Itself, except for you'd have to multiply it by negative 0.05. But we can use the calculator, so let's not worry about it. Alright, so if I want to take the first derivative, since I've got it into y equals, it's in y1, I really am just going to type the same thing in, except for instead of x equals 10, I want x equals 15. And so we get negative 5.5269. So S prime of 15 is negative 5.527. Alright, so this is not S. S, so if we had a graph of S, whatever it looks like, it should be exponential and decreasing there, but it doesn't matter. So what is your x coordinate, or your x value? What does it stand for? It is days. And then what is on the y-axis? It is tons. So this equation, if you want to know the weight at a certain time, you would plug in, if we plugged in 15, it would give us the weight at 15 days. But we're not finding S of 15, we're finding S prime. So it is a rate of change. So, okay, so you are losing 5.527 tons per day at this particular point. So you have to say at 15 days, and make sure you say at 15 days or on day 15. It needs to be language that specifically means that point in time. You do not want to say something like over the first 15 days, because that talks about the whole time period from 0 to 15. I think it'd be okay to say after 15 days, but you wouldn't want to say something like during the first 15 days or over 15 days, because you want to make sure it's at that particular moment in time. So at 15 days, the weight of the sand is Since it's negative, we got to say decreasing at a rate of, this is really important here, do not put a negative right here. They will count it wrong if you put a negative right there. Decreasing covers the negative. So if you say it's decreasing at a rate of negative 5.527, they will count it wrong. You could probably say that, but I'm not certain. You could definitely say this. I'm thinking they might not accept increasing, because increasing at a negative rate at best is really confusing and is maybe wrong because it's not actually increasing. But you could say that the weight of sand is changing at a rate of, and then use a negative. So changing does not imply positive or negative, so you could say that. But if you use the word decreasing here, you cannot use a negative over here. So just be really careful with that whenever you do this. And then we need units, which is tons per day. All right, now, I really don't like second derivative ones, but they ask you about this sometimes. So, first let's find the second derivative. So, to do that, what we can do is what we just did. We can leave it in there, and I think we can do this. I think we can derivativize it twice. I think what we'll have to do is we'll do derivative of derivative, and then we'll have to put comma x and close that parentheses. Let's see if it works. It does. You cannot put 15 in, because if you put y1 to 15, it'll plug in 15 before it takes the derivative, which means that you'll just have a number, so you'll get the derivative of 0 every time. Like if I do this, if you do it with, I'm pretty sure that's what happens. Yeah. So what it does is it plugs in 15 to the equation, which gives you a number, whatever it might be. So if you've got like 6,000 or something, when you take the derivative of 6,000 or 10,000 or negative 283, it doesn't even matter what number it is. Derivative of any number will be 0, so it wouldn't matter. So you have to have the x there, so it'll take the derivative first, and then you do the x equals 15 on the end, where it'll plug it in after it's taken the derivative. So we're getting s double prime is 0.276. So s double prime of 15 is 0.276. Now, I do not like these problems. They are so confusing to write out what they mean. All right, so this is the derivative of s prime. So we're finding the derivative, or the slope, of s prime. So, yeah. Yes, so we got days here. We got tons per day here. And this tons per day, that's your rate. The S is changing. So, you have to say at 15 days, the rate of change of the weight of sand, the weight of the sand, is, you could say increasing, I'm going to use changing this time, is changing or you could say increasing since it's positive, at a rate of 0.276 tons per day. So, whenever you see second derivative, it's got to, assuming that the original was just the amount, it's got to be a rate of a rate. Yes, Laura. Usually it's going to be a 2-point problem. Yeah. So usually you get a point for getting the correct answer using your calculator, and then you get a point for explaining what it means. Okay, questions? All right. Depth of water in a rain gauge is given by the twice differentiable function. Here, R, it's measured in inches, and time can be measured in hours. Values of R prime of T, the derivative of R, are at selected values of time, are shown in the table above. Below, actually, that should be changed. It is known that the graph of R is concave down from 0 to 5. First, this is like a free response question that you would see. Is there a time from 0 to 24 at which the depth of the water in the rain gauge is changing at a rate of 0.5 inches per hour? Justify your answer.
Yes, intermediate value theorem.
Okay, this is intermediate value theorem. Thomas is right. Because it tells us that R is twice differentiable. So we would start off saying since R is twice differentiable, R prime is continuous. And also differentiable, but that doesn't matter for intermediate value theorem. You don't have to say that it's differentiable. If you said it here, it wouldn't hurt. Therefore, since you can see that really you can use any value here between 0 and 12, or really over here, it really doesn't matter. You can just see the very highest is at 15, right? Where you're at 0.55. Pretty much everywhere else, it's below 0.55. So you could pick really any of the other values here to show that that's below 0.5 and that R prime of 15 is above 0.5. So I'm just going to use R prime of 0, but you could use literally anything else except for R prime of 15. So you're going to say R prime of 0, I like to put which equals 0.3, is less than 0.5, which is less than 0.55, which is R prime of 15. It's going to come up later for another part of this problem. So it doesn't matter here, but it's going to matter later. So we have this. We are basically just going to restate here the depth of the water in the rain gauge. must be changing at a rate of 0.5 inches per hour for some time on 0 less than or equal to t less than or equal to 24. And again, you could use something besides r prime of 0. You could use r prime of 2, 5, 12, 18, or 24 here. Because all of those are less than 0.5. Alright, questions? Alright, so that's the same information at the top part. Use the data in the table to approximate r double prime of 16.5. Show the computations that lead to your answer using correct units. Explain the meaning of r double prime of 16.5 in context of the problem. So, we're given r prime in our table. If we're trying to find r double prime, that would be the slope of r prime. We only have points here, so we can only estimate. How could we estimate r double prime of 16.5? Slope between 2 points, and you're going to use 15 and 18 here because those are on either side of 16.5. So you would just do 0.4 minus 0.55 over 18 minus 15, so you get negative 0.15 over 3, so that would give you negative 0.05. Okay, so that to me is the easier part of this. Now you got to explain what that means. So let's think about, we're taking the derivative of r prime. What is r prime? Is inches per hour, which is the rate of change of the height of the water. So that is r prime, right? Rate of change of the height of the water is r prime. We just found the rate of change of that, the slope of that. So we would say at 16.5 hours, the rate of change of the height of the water is, you can either say changing or decreasing here. Since it's negative, it's going to be decreasing. I'm going to write it this way just so you see the different ways to write it. Is changing at a rate of negative 0.05. And that is going to be inches per hour per hour. So do your y units over your x units. Inches per hour per hour. It is okay to use the negative here because I just said changing. I did not say decreasing. If I use the word decreasing, I do not put the negative with my number there. We probably should have said is changing at a rate of approximately But I don't think that's something they would count off for here. I think you could still get credit. Yeah, I know it's okay here that like if you use equal signs instead of the approximation symbol, so I'm going to extend that to think that it doesn't matter if you use is or is approximately here. But to be more precise, we probably should say approximately. All right, we have. We got to do this. All right. So at time t equals 2, the depth of the water in the rain gauge is 0.8 inches. Use the line tangent to the graph of R at t equals 2 to approximate the depth of the water in the gauge at t equals 3 hours. Is the approximation an underestimate or an overestimate of the actual depth of the water at time t equals 3? Justify your answer. Okay, so we don't know the equation of R, right? They have not given us the equation of R, but if we picture that we have some sort of equation R here, and we know at time t equals 2 that we've got this tangent line. If we use that to approximate at 3, it's not going to be the exact thing, but it might be close. It's as close as we can get with the information that we've got here. So they are telling us that at time t, the depth of the water is 0.8, so that tells me that R of 2 is 0.8. So there's my point. So 2.8 is my point for my tangent line. My slope is going to be R prime of 2, which is given to you in the equation. So that's just, in the table, that's just 0.2. That's your slope. Here. And so how do we write the equation of the tangent line? 0.2 x minus 2 plus 0.8. It is best if you use the approximation symbol here, but again, I don't think they're going to count off if you use the equal sign. So this is your tangent line. If you want to use it to estimate at 3, you just plug in 3. All right. So y about 0.2, 3 minus 2 plus 0.8. So 0.2 times 1 plus 0.8. It's going to give us 1 there. So, and this is 1 foot, right? Inch. We are going to have to do some writing, but not for the part of the problem we've already done. The part we have to do, this is all you need for this part. Overestimate and underestimate is where you've got to use some writing. So, is the approximation an underestimate or an overestimate of the actual depth? Justify your answer. What do we care about when we're talking about overestimate or underestimate with tangent lines? Concavity. And that is why they gave us graph of R is concave down. So my picture is actually wrong. My picture is correct. We are concave down here, meaning the tangent line is going to be above the graph. So we would say since R is concave down for 0, what's it say? Less than or equal to, or just, yeah, less than or equal to x less than or equal to 5. The estimate is an overestimate. When they say justify your answer, you've got to mention concavity there. You would have to write it out still. Okay. We don't have time for this. We're going to skip that one. Alright, so. Alright, star math. You will need. Alright. It is not a grade. I really do want you to do your very, very, very best just because I want to see like what our top ability is. We're probably going to run out of time. If you run out of time, I'll let you take a few minutes at the beginning of class tomorrow to finish it. Yes. Yes.
It's calculator and active.
If you need your calculator, there will be a calculator or if it's calculator active, there'll be a calculator that shows up on the computer screen. So you cannot use a handheld calculator. You can only use what they give you in the test. Okay. So you will need a piece of paper to work out some problems, although the first ones might not need work. If you go to the Elkin City Schools website, it will pop a calculator up on the screen if it is allowed. The district has purchased this. The idea is so that I can see where you have gaps and holes and what, but really, honestly, calculus. I mean, honestly, I have a pretty decent idea of where you're weak and where you're not, and this is probably not going to tell me a whole lot. So let's just treat it as a personal challenge to see if we can do really, really great on it. Okay. Okay, Elgin City Schools. Everybody watch so you know where to go, including Thomas. Alright. Alright. Elgin City Schools website, go down to the bottom where it says links. Click on student links. It's got to be on Elkin City Schools, not Elkin High School. Then you're going to click on, under EHS, you're going to click on Clever Portal. Don't try it, please. Alright. Alright. Then you're going to do Star AR Renaissance, this one. And then from there, you'll log in with Google, then you're going to do Star Math. Mine looks different from yours from there. Don't do the pig. The pig is Freckle Math, which they have also paid for. We're probably not going to use that a lot unless they make us.
We're really going to when we put check.